In our lecture series on the occasion of the 50th anniversary of the computer science curriculum at KU Leuven, today we will be looking forward. We will be looking towards the future. So how will computer science change your life in the next 50 years? What will be the hot topics in the next decade and beyond? To answer those questions, we have invited 5 of our very own faculty members, the best of the best. And they will explain what they are working on today and how that will play a role in the society of tomorrow. So without further ado, let me introduce our first speaker, Professor Tom van Cutsem. Tom joined the department recently in 2022. He obtained his PhD from the Free University of Brussels, where he also held an assistant professorship for some time. And before joining the department, he had a career as a senior researcher and department head at Nokia Bell Labs in Antwerp. He's a member of the Distrinet section, and he will address the future of the cloud, the web, AI, and IoT. Tom, it's up to you.
All right. Hello, everyone. Good evening. So I'm Tom van Cutsem, indeed. I'm a professor here in the computer science department. I work in the Distrinet research group, and today I want to talk to you indeed about the future of some of the topics that Stefan mentioned. And another way to frame it, actually, is that we're going to look at the future of software through the lens of cybersecurity. And we're going to take a view from Distrinet, a view from from my research group. Now, this title, A View from Distrinet, is actually inspired by the reports that came out of UC Berkeley, University of California at Berkeley. I'm pretty sure my colleagues will know what I'm talking about. It's one of the most prestigious computer science universities in California in the US, and their faculty regularly publishes these forward-looking reports on research areas like this one, on parallel computing. And they also call their reports like, okay, a view from Berkeley. And honestly, it's not just a view from Berkeley because they're esteemed faculty. It's also because they actually do have a fantastic view in Berkeley. So this is a picture taken from the campus. I don't know if you've ever been there. It's northeast of San Francisco. So you see the iconic tower of the campus. You see the Oakland Bay Bridge, not the Golden Gate. That's a bit further to the right. And you see a beautiful panorama of the skyline of San Francisco. You see the Trans-America Pyramid and the mountains and so on. Beautiful view. So I'm going to present you the future of software through a cybersecurity lens, a view from Distrinet. And, well, let me put it this way. The view from Distrinet certainly is not the same as the view from Berkeley, at least the physical view. So I guess I will have to make sure that the view from the faculty is at least worth it. And so you know also which side of the building I work on. Now, joking aside, the view may not be that nice, but the people are fantastic. So this is the full group picture taken earlier this year. As you can see, it's a pretty big research group, very diverse. So what are all these people working on, actually? So when we talk about the research in the group, we typically describe it as being structured according to 3 pillars. So secure software, distributed software, and software engineering. These are the core topics in the group. But don't be misled to think that each of us works on only one of these topics. In reality, people work across these domains. These are not silos, right? If you ask the question, okay, Distrinet, what type of research are you doing? Is it very fundamental? Is it very applied? It's actually both and everything in between. We do research going from very fundamental over strategic research, applied research, all the way to spin-offs. And just to give you a few examples, so this is my colleague Dominique de Vrieze. He has an active ERC grant. ERC grants are the most prestigious fundamental research grants you can get, awarded by the European Union, and he's working specifically on formal security guarantees for the instruction sets that come in our hardware. Very, very interesting work. Now, most of the research we do actually is more strategic basic research, and so within Distrinet, we are working in and actually leading a big initiative funded by the Flemish government called the Cybersecurity Research Program. So, you know, cybersecurity is a big and active topic, and we are spearheading that initiative along with our colleagues from COSIC in the ASAT group. So that's regional, also in the European Union. So in the EU, we have several projects where we look, for instance, at applying AI to cybersecurity, both attack and defense related. We also have very applied research. Also, actually, for instance, one example in the area of AI and cybersecurity is the work of my colleague Lieven de Smet. And I believe Pierre talked about this also as part of his lecture. And so Lieven worked on a system that can use machine learning to detect when people register domain names on the internet, whether those domain names might be used for malicious activity. And this is a system that's now been in production for several years at OurResearchers, and OurResearchers is the top-level domain registrar for .eu domain names. And today, Lieven is working with the Center for Cybersecurity Belgium to repeat some of these tactics to combat phishing. And then finally, we have spin-offs. We have several. I guess most of you know Wouter Joosen. He's the head of our group, and he founded this very successful spin-off called Ubizen, but there's been many others since. I would be remiss not to mention some of the impact our work has had on the industry, and in particular the work of my colleague Matti van Hoof. So Matti is a world expert on Wi-Fi. I guess you all know what Wi-Fi is, right? You use it on a daily basis, at home, at work. Well, Matti discovered not one, but multiple flaws in the Wi-Fi protocol. And this, as you can see, garnered quite a lot of media attention, and today Matti is a well-respected and consulted researcher on network security, Wi-Fi security. So that's enough about the group. Now let's look a little bit forward in the areas that Distrinet is working on. What are some of the hot topics, and where do we see the fields evolving? And I'm going to address 4 of them: cloud, web, AI, and the future of software engineering. So let's start with the cloud. I guess most of you know what I mean when I say the cloud, not physical clouds, but virtual clouds. And you all know what I'm talking about because all of you use Microsoft 365, and at work you use Google Docs and Gmail and all these kind of things. That's all software running in the cloud, right? If you're an IT person, you all know about these services that Amazon AWS and Azure that they give you to develop software that runs in the cloud. But what is the cloud really? Well, the cloud is, of course, a bunch of buildings, data centers, like this one in Saint-Guilain in this country, operated by Google. If you go inside, then you see these things, right? Racks upon racks upon racks of servers. This is where this actual software is running. And when I talk about the cloud to my students, I also always show them this picture from the Free Software Foundation. And what it says is, there is no cloud, there is just other people's computers. And of course, this is factually true, but what it hints at is the fact that, and maybe you haven't thought about that, but we really need to trust these service operators to be very secure, right? If Microsoft and Google and Amazon don't do their job, they're going to compromise our data and our applications. And of course, these companies are probably not the ones that we have to be afraid of, but when you're running your software in one of these machines, you are not getting exclusive access to these hardware resources. There's other customers of these companies, which can be anyone, that is running their applications and their software side by side with yours. And that actually creates a lot of security issues. And this is actually something where the cloud is evolving towards what the marketing people call the confidential cloud. So the confidential cloud or confidential cloud computing is the direction where these hardware vendors and the software players, you see all of their names and logos there, they're trying to found what they call a confidential computing consortium to create all kinds of solutions to make sure that when customers run their software in the cloud, that they remain nicely isolated. And if you would go and read up on what is behind confidential cloud computing, you will eventually end up reading about trusted execution environments or secure enclaves. And this is the core technology that sits inside of your hardware in the CPUs and in the operating systems. It creates kind of like a secure vault or an enclave where your software can run securely, even if the person running the computer and controlling the operating system is potentially malicious. And this brings me to the research going on in the group by Professors Frank Piesen and Jo van Bulk. Jo is also a new faculty in the group, and both of them are world experts in understanding the security of these secure enclaves. In particular, what they're really good at is figuring out what are all the possible bugs in this whole complex system stack so that you can still enter into the secure enclave that everybody thinks is secure. And in fact, they also have participated in several attacks that made the headlines because they broke not just any research prototype, they broke the CPUs that are sold by companies like Intel. And in fact, Jo just last year received a Cybersecurity Artifact Impact Award for the tools that he built to help security researchers security systems. Okay, so that's the future of the cloud. So this technology is improving, and in the future we will have more secure clouds, I'm sure of that. So let's switch gears a bit and talk about the web. The web is another software platform that all of us use on a daily basis. And the web has undergone a tremendous transformation in the last decades. Some of you may be old enough to remember, right, the very early days of the web, Netscape, Internet Explorer, the first commercial browsers. Actually, the web itself got started in 1989 by Tim Berners-Lee at CERN as a way of building a system to help researchers share their data and experiments more effectively with each other. Then afterwards, it became commercial, and then people started using it to build websites and so on and so forth. Now, in the early days of the web, it was very difficult for a regular person to participate in the web, to set up your own website, technically very difficult. So most of us would just consume content on the web. We wouldn't produce. And the web back then was also very open. Open protocols, TCP/IP, HTTP, open protocols that anyone can participate in. And as the web grew and matured and more money got involved, we saw a shift from this open web to a web that is controlled by large corporations. That's still the world that we live in today. That's the Web 2 era, where we have the emergence of web platforms, and you all know these. This is the Facebooks, this is the Twitters, this is the YouTubes. And when you use these platforms, as you know, you have to sign up, you have to create an account on their platform, and in exchange, you get fancy tools to make it very easy for you to produce content. So the web became not read-only, but read-write. So now it's very easy for everyone to create content on the web. The flip side, or the dark side of this evolution, is that the web is now built no longer on open protocols, but on corporate protocols, right? It's all of these platforms, they build on proprietary stacks, which is why these companies are, of course, so valuable, right? Why they are so highly valued. Now, today, some people say that we are at the cusp of another transition of the web, and some people call this Web 3, because it's sort of the third big wave. And Web 3 is all about people, users, organizations taking back control, owning their own identity, owning their own assets on the web. Now, this is something that started with the invention of something called a blockchain, and that was actually invented as part of a little project that you might have heard of called Bitcoin. So Bitcoin was the first cryptocurrency, and it enabled peer-to-peer money transfer on the web. Some people call it the TCP/IP of money, right? TCP/IP of money is a good point because the protocol is indeed open. Anyone can participate. That's what distinguishes these protocols. And in doing so, they made the web read, write, and own. You can now transact on the web. And this ties into some of the work that I do in the group, which is looking at something called smart contracts. Smart contracts are programs you can store on blockchain networks and that execute in a trustless way. And why are they useful? Well, in a traditional system, if Alice and Bob want to transact, say, send money to each other, sell their house, you always need a trusted third party in the middle. You know these trusted third parties as banks or as notaries, right? smart contracts actually allow you to do peer-to-peer transfers through intermediated code called smart contracts, which are where the code actually describes all of the conditions that need to be satisfied for Alice and Bob to transact. And these pieces of code, they run on these blockchains, so nobody can change them at will. So they are trustless. And so now, of course, these smart contracts, they deal with money, or they deal with assets, valuable assets. And if there's a bug in your code, and of course programmers do tend to make bugs, then the consequences can be quite disastrous. And here's a chart that I took from a recent report studying cybercrime using cryptocurrencies and the like. And as you can see, sort of the value stolen from these contracts is skyrocketing, with billions of dollars now being extracted from these contracts. It's kind of like a modern way to rob the bank, right? You no longer need to physically go there with a gun. You just need to have programming skills, find the bug in the contract, and you get the money. That's the thing. So we're working on better ways to write these contracts, new software tools, new programming languages to make this more secure. Right. So third topic, and I will be very brief, is AI. And we'll hear much more about AI later. But if you've been to the talks from the previous lectures, in particular Inti de Keukenlehre, you will know that AI has a lot of issues. It creates a lot of new attack surface for applications. Imagine, companies using chatbots to interact with customers, the customers asking certain kinds of questions. If the chatbot has access to company proprietary information that they shouldn't leak, the user just asking questions in a certain way can make it so that the chatbot is going to reveal that information. So Inti gave a lot of demos, so I will not belabor the point here. We have two brilliant postdocs in the group, Tim and Thomas, and they are cataloging all the risks related to large language models and also mitigations. And they have a blog called Blue 41. If you go to that website, they have a lot of content, interesting content, describing the latest attacks on these AI models. Okay, so the last thing I want to talk about is not the future of certain platforms that we use to build software, but actually, how will we build software in the future itself? How will that change, or could that potentially change? And here, I venture into the domain of my colleagues Bart Jacobs and Dominique de Vrieze, who are experts in formal verification of software. So formal verification is this idea of you have a specification of your software, typically written in some kind of logic, you have your code, and you would ideally like to know, does my code actually satisfy this specification? It's a very difficult thing to do in general. The situation has improved with leaps and bounds in recent decades, so it's going to be interesting to see where this technology will be 50 years from now. Just to make it a bit more concrete, so we are working in Distrinet, or Bart is working on a tool called VeryFast. VeryFast allows you, using formal verification, to detect a lot of very pernicious bugs. The screenshot that is shown there, you don't need to understand anything about it, but it shows a screenshot of a bug called Heartbleed. And Heartbleed was a bug that affected secure sockets, or HTTPS. So every time you create a secure link on the internet and you see the green icon in your browser, you're using this OpenSSL library, and they had a bug that completely compromised the security. And if they would have coded using Bart's tool, they would have found that bug. And so these tools, they help you find these bugs. Okay, so the final thing to say here is that there is good news on the horizon, which is that most of these bugs are in code that is written in C or C++. Many of you will know what I'm talking about. Low-level systems languages, and they're very unsafe. But this is changing. So here's a chart from GitHub. You all know GitHub, the open source company. So they publish every year charts on most popular languages that are growing in popularity. And in the last few years, at number one for a couple of years now is Rust. Is a new programming language that is as fast as C and C++, but is way more secure. It completely avoids all of these bugs. So as we transition in the next few decades, I'm pretty sure we will see software that is just much better designed because it's written in much better programming languages. Okay, so that kind of concludes my talk. I hope you took something away from it. Of course, predicting the future is hard, so no guarantees here. I will leave you with a quote from a fantastic computer scientist, one of the founding fathers of the PC, Alan Kay, who said that the best way to predict the future is to invent it. And so I think that's what I wish for the computer science department for the next 50 years. Let's invent the future together. Thank you very much. Enjoy the rest of your evening.
So our second speaker is Professor Adalberto Simeone. Adalberto did his PhD in Bari, Italy, and held postdoctoral positions in Lancaster and Portsmouth in the United Kingdom. He joined the department in 2017. He's a member of the Human-Computer Interaction section, and he will talk about our future meta-lives in the metaverse.
Good evening, everybody. So my talk is going to be a lot more about hopes and dreams. So because that is what the metaverse is about right now. Oh, yes, the microphone. Yes. Yeah, so is it still happening? That is the question, or maybe some of you, at least I hope, still have. Like, is the metaverse still a thing? Do we need to care about the metaverse? Well, hopefully the answer is going to be maybe at the end of this talk. If anybody is not familiar with the metaverse, I'll just give a brief introduction. So the term metaverse comes from a science fiction novel that was set in the 21st century America, where much of the power of the American government was ceded to corporations, and it had become a dystopian capitalist nightmare, so very fictional, let's say. But in this imagined future, so the protagonist had the possibility of entering the future of the internet as the author imagined it, which was an actual physical location in the web of that future, like a three-dimensional environment that people could enter in and live a different life. And this, in the context of the novel, is where the story happens. And this topic, this concept of the metaverse as a separate three-dimensional environment in which we can live, has continued to gain popularity in movies and other media. For example, maybe some of you remember movie Johnny Mnemonic. Here too, the metaverse was actually a three-dimensional city where there were buildings you could explore, you could move, and you had an identity in it. Much more recently, we have the movie Ready Player One, that also was based on a science fiction novel, also about a dystopian future. But this is probably much more closer to the idea of the metaverse as we imagine it today. So a future three-dimensional environment where every kind of world, every kind of application exists together in this shared online environment. Then the lives of the people who then join the metaverse are much worse. But in the metaverse, they can be whoever they want to be and do everything they want. Also, if there are some gamers in the room, maybe you're familiar with Cyberpunk 2077. There's also a metaverse there, and it's much more dangerous location. In fact, AIs, in the context of the game, have run amok and have conquered the internet. So there's like a cyber wall that blocks everything, and every system is disconnected from each other, save from a few brave souls that try to go and breach and enter this kind of wilderness in terms of the metaverse. But in some of the defining characteristics of the metaverse, as we might see in the short term or in the near future, are that it is a single online world, an immersive internet perhaps, where users retain some form of individual identity. In fact, it's a popular trope that hackers or net runners, in this kind of media, can affect that. And you also are aware of it, of how dangerous it is to have our identity stolen in the non-metaverse internet. So maybe that is maybe, I don't know, that is one of the characteristics that people think of when thinking about the metaverse. And that there must be a very distinct separation between the metaverse and the real world. That is perhaps not something that we might see. In fact, we are probably going towards some kind of a blended future where there's no really separation of virtual and physical content. Perhaps as Mark Zuckerberg said, one of the most important characteristics of the metaverse is that if you die in the metaverse, you die in the real world. But after that, you might be aware of, there was a lot of interest in the metaverse in recent years. No? Especially at the height of 2020, 2021, coinciding with the COVID pandemic, there was the idea that very soon, we would have been, in the metaverse, every one of us, and then the world went back to normality. But you still see that there is a lot of interest in the metaverse right now. Mistakes were made. So I don't know if you can hear. Yeah, you can probably not hear much. So this is a metaverse party that the EU threw in the metaverse, but hardly anyone turned up. And I love the European Union as much as probably everybody else is in this room. But I can think what would have happened if this money was spent a little bit better. But what kind of metaverse can we enjoy today? So maybe you are already in one of them. No? The browser, could it be a metaverse analogy? No? The modern internet probably best approximates the concept of the metaverse. What we do on the internet has consequences in the real world. However, it is not immersive. But does it need to be immersive? We'll see that there are some reasons why this is an important characteristic. And what we can think of more exactly is that there are metaverse islands. Right now, there are several distinct metaverses. Some of you might remember, there still is a thing, like World of Warcraft, Minecraft. Maybe some of you have heard about Second Life or VR Chat. So these are some of the metaverse environments that we can join right now. Maybe if you are as old as me, you might even remember this. This was, before World of Warcraft, there was Ultima Online. This was an online role-playing game where people could, join and have their alternative lives in a fantasy environment. It was one of its kind, probably the precursor of many of the massive multiplayer online role-playing games that came after. And when I was at the time, I even had a guild. I managed an online guild for Ultima Online. Maybe bonus points if you know what I'm talking about. But then came Second Life. Now, Second Life is probably another best approximation of the metaverses of today. It's also an online virtual environment where people can have their life. But it was not immersive. There was when Second Life came about, there was a lot of interest. For example, people were starting to buy lands in Second Life. I think the Belgian government actually had an embassy at the time of Second Life. There was also a lot of interest in education, online virtual environments where we can teach and have lectures and so on. But it was an application that you enjoyed or you joined while on the desktop. It still is active. Then, after the revolution or the second renaissance of virtual reality, the interest in virtual reality was, grew in popularity, and one of the surviving applications that came about in those years is VR Chat. So this has given rise to a lot of different community that, day after day they meet in the metaverse and have actual meta lives. So there are people out there, maybe even in this room, that will go on the metaverse and enjoy their alternative lives there. Maybe your children will be familiar with Roblox. This came after my time. I'm much more of a Lego fan, so I'm not entirely familiar with Roblox. But this is something that's very popular with children of today. They can enjoy, playing together with their friends. There's also a VR version of Roblox. And While with Second Life, you could also buy money. There was a currency that the authors of Second Life introduced. There is the conjunction with crypto. That was also mentioned in the previous talk. Maybe you know of Decentraland. Decentraland is a crypto project where you can buy land in Decentraland through a cryptocurrency that is called Mana, and through this you can access various services. The problem is that nobody is there to buy from. It's just empty spaces. I've been there a few days ago, and it was just me. This is something that we actually did. So we brought about meaningful change into the lives of the students. So during the coronavirus pandemic, we had one of our a course about virtual reality that was held in virtual reality. And I maintain to this day that this is how the VR course, every VR course should be done. If we professors of VR don't give the example, then we will. But then again, we went back to the real classroom, so we took a step back. So what we did is that we used an online environment, and we met there because we couldn't met in the physical environment. And I think I am the red guy in front, and the other were other students of the lecture, and we met there, and we gave the lecture there. We interacted and collaborated together during this time. So this is certainly something that we can see more in the future, especially if you think about remote participation and so on. Of course, there is the angle from the companies like Meta that are their own angle in this. And I will let Mark talk for a little bit. So he is showing a vision of what he thinks the metaverse might be.
Imagine your best friend is at a concert somewhere across the world. What if you could be there with her?
Sneakers, I never had a car.
You're here.
Tell it like it is. Love how you live. When you're doing what you're doing, just tell the truth.
Maybe already you can start to see what some of the problems with this are, but let's continue to watch the video a little bit. Maybe.
After party passes? Yes.
I want you to tell it like it is. Love how you live. When you're doing what you do, just tell the truth.
After they go back to their sad lives. Now, what if the metaverse was there to help us, to provide something more interesting to do?
What if there was an after party that anyone could go to, no matter where they were?
This is wild. Hey, check this out. Charity auction happening. Oh, there's swag.
And when you go to the after party, you could connect with other fans, hear new versions of your favorite songs, and check out the merch that just dropped.
Ooh, I like that one.
Well, now you've got to get it.
You can start to see how
it's about selling stuff.
Like this.
But hopefully there's something better than this. Something wrong with... Okay, so yeah, of course, in the vision of Mark, it's maybe some way of selling more stuff, more swag, as the young of today say. But maybe you can start to see some of the problems in that video that you saw. Like, for example, how was the person that was elsewhere, not at the concert, how were they able to appear in the middle of the concert? Are they a hologram? Is there a projector somewhere? Then you have seen that they were sitting on the couch But in the metaverse, no, they were walking, they were interacting with people. So how is that going to happen from an actual interaction perspective? And then at the end of the day, us researchers or us developers of VR application have to actually build this stuff. And unfortunately, it cannot really be done. Nobody has an idea why, because if you start to walk in your room, then at some point you will hit the wall. And that is the classic problem of virtual reality, right? So there have to be some solution that we need to find. But right now, there are people, as I said, that are using the metaverse. For example, an argument can be made that the immersivity of virtual reality cannot be beat in comparison from a Teams call or a WhatsApp message. No, in VR, you can really be there with the other person. And if you think about people that live, for example, far apart, no, VR brings that dimension that you cannot get otherwise. Then for some people, they can use the metaverse to truly express themselves as they are. So there are several people who live one life in the real world, in the meet space, and a different life in the metaverse, where they can actually be who they see themselves as being. Perhaps digital twinning can be another alternative for the future, where maybe you can have like a digital version of the city in which you live in, which would help discoverability of new services, new people, and so on, in a way that the current internet maybe doesn't enable to do as well. And it will also give rise to new social phenomenon. Maybe you haven't heard of this before. So in the metaverse right now, there are so-called sleep worlds that are environments where people go to fall asleep together. So people that live in all parts of the world, they go to this world, and then they sleep while wearing the VR headset, because that gives them the idea, the emotion that when they wake up, they will be with other people, and that is some unique phenomenon that only came about with the metaverse. And one of my students just yesterday told me that there is also hugging worlds where you can go and there are other people that hug you, just at random. Yeah? And research is also not wasting any time. They are exploring a lot of different directions. So one important aspect is personal boundaries or social harassment in VR, because in VR you have a body, you have a three-dimensional body. And although no physical arm, even though Mark Zuckerberg might think otherwise, you can't die in the metaverse, but people can touch you. So you have a three-dimensional body, and if there is no software barrier that stops that from happening, people can come close to you and do things that you might not want them to do. And also there's a lot of more interaction to be built. Our research group has also done some investigation of this space. For example, right now you can't really do like even a handshake in VR or hug somebody, because the interaction for that is not yet there. Usually you emote by pressing a button and then your avatar does like a gesture or something, because the headset that we have don't support really that kind of interaction. And also, some people have noticed that the metaverse looks very bland. It's a recreation of real world. So we are also looked at how how the metaverse should be built and what kind of features the metaverse, architectural features the metaverse should bring about. Because in VR we can do everything, we can be everybody, and there's no requirement, for example, to have a roof in the metaverse if there's not going to be any rain that can wet us, So that brings about, more creative potential for at least for the design of the metaverse. So in conclusion, is the metaverse still happening? Yes, I think so. The metaverse is still going to happen, but it will likely be a gradual transition more than a sudden change. So when the metaverse will happen is the day in which you will be able to have an immersive experience with the same degree of ease and that you have today by just taking your phone out and checking something on your phone. When you will be able to do that with VR, then you will already be in the metaverse and you will probably not have realized it. Okay, so that was all for now. I hope you enjoyed it. Thank you.
Our next speaker is Professor Vero van den Abelen. Vero has a background in product and interaction design with a PhD in the social sciences from KU Leuven. She became a faculty member in 2018 on Campus Group T in the Faculty of Engineering Technology. Vero is the head of the Human-Computer Interaction section, and she will address both the history and the future challenges of her field. Vero. Yeah, use this one.
Sure, I don't go over time. Yes. All right. Good evening. It's an honor to be here and to be allowed to entertain you on the history and the future of human-computer interaction. I want to start with a question. Whom among you has had a formal training or has had a formal course on human-computer interaction? Okay, that's what I anticipated, so that's how I also built this session to actually introduce you, so in 50 minutes you have a bit of an understanding of this field. Because it is a young field, and we are also at the Department of Computer Science, we are the youngest research unit. And so I'm going to walk you through the history and the future, and quite often if you think about this evolution, it's sort of a presentation of technology became more advanced, and so it supported interactions that were more advanced and more advanced. I'm going to do the opposite. I'm actually going to introduce you to several visionary thinkers, and they had a certain vision of how computers should support interaction, so they had understandings of what interaction should be, and from that vision, they steer technology. So I'm actually going to try to convince you that rather than technology supporting interaction, it was new understandings of interactions that supported, that steered technology. But you can debate after, during the reception, whether you agree or not. I'm also not going to focus on all visionary thinkers because we don't have time for that. Since my own research topic is on smart gamification, I did also embed a little quiz. So there are certain slides with question marks where I'm going to invite you to guess who the person is or what the product is that I'm talking about. And if you guess all of them, you have a score of 10. So you can perhaps have 10 out of 10. We'll see. Yes. All right, but let's start with the start. So if you see that question mark, there's something for you to guess. And we're going to start with the beginning here. So we're going 50 years back, as this is 50 years of computer science. And actually, we're going even a bit farther back. The Rekencenter, if I'm correctly informed, it was created here in 1961. We had IBM 1620, and that really was that first computing paradigm of large-scale computing. So maybe for some of you, this triggers memories, yes. I don't know who here in the audience went with these punch cards to this one computer that was to be shared with everyone at this university. Now, in this paradigm, in this understanding of what computers were, a computer was only to be operated by the cleverest of men. Yes? You had to have a training, a university training, maybe even more, certainly not people from social sciences could touch this computer, yes? Only the cleverest of men, and you had to share that one computer. And actually, you couldn't even touch the computer itself because you gave your punch cards to an operator that would feed it into the machine, and a week later you would come back and you would find out whether your code ran or not. I'm not going to spend too much time on this because actually this is not where the history of human-computer interaction began. Here, it's still that paradigm of men that have to adapt to the computer, not the other way around. So then where did it really start? Well, we're moving along, and we're 1969, yes? And here comes a slide where you can guess who is on this slide. Yes, I see some people nod, yes. Dennis Ritchie, Ken Thompson, and I'm talking about Unix, yes. And yes, I know there was Multics and so on, but Unix, this is really where HCI, human-computer interaction, HCI began. Why? Well, Unix had a lot of innovations, that is kernel in assembly. It had this interesting way of dealing with files, sort of creating virtual memory, but it also had a Unix shell. Dennis Ritchie and Ken Thompson had this idea that it should no longer be that users, that these smart men, computer scientists, smart women, had to use punch cards or had to use these low-level machine languages to converse, instruct computers. So they created this Unix shell. And all of a sudden, you can instruct, you can command, you can converse with computers, you can dialogue. So this is where it began. We're sort of 60s, 70s, 80s. We call these command line interfaces. And so now computers become more accessible. But of course, it's still this professional computing paradigm because you have to study this, right? You have to study the command sets. And this is, for example, a typical study from that period where there would be studies on, okay, how do we design these command sets? And is it better to have very short commands that are acronyms, or should we have longer commands that are more descriptive? What is least error prone? What is most efficient? I know the outcome of this study. If you want to know the outcome, you have to come ask me in the reception. Okay, but so we're moving on. We don't have much time. And I want to move into the area of personal computing. And you would think that I would fast forward. Yeah? So we were 1969, but I'm actually going to go back in time. And I'm going to go back to 1963. And this still really blows my mind every time. I don't know, are there people who knows who is on this slide? Yeah, some nods. And what I am showing? So this is Ivan Sutherland, and this is the Sketchpad. There was a PhD student at MIT who demonstrated this kind of program computing application where you could actually do some computer-aided drawing with a light pen. It was still programmed in Fortran, but it actually paved the way for object-oriented programming. Yes. He used this notion of objects and instances and inheritance, which inspired Simula, which was then the first real object-oriented programming language. But it also really changed the understanding of what computers could do, because you no longer needed a keyboard. You could actually directly draw on a computer. You could point at a computer. Computers could maybe be useful for artists, for architects. So this changed this paradigm of computers being only for people that had a training in command line interfaces, in these command sets. Now I am fast forwarding, but only a couple of years. Yes. Maybe you know who this person is on this slide and what he's showing. Yes. Douglas Engelbart, and that's the Augment NLS. One of the research groups here is inspired by this. He gave the mother of all demos in 1968. He showed there actually a graphical user interface. He showed also something peculiar here that he's holding. And he said, yeah, it's this thing, and you can actually move a pointer on the screen, and we've decided to call it a computer mouse. It stuck with us. So I'm not going to walk you through then all the other stuff, Xerox PARC and Steve Jobs and so on, that bought the IP out. Yes, but that was still later. The founding fathers were really in the 60s. So in 1962, in 1968, we already had this research where you were seeing graphic interfaces, graphic user interfaces, and direct manipulation. The idea that you don't have to instruct and type, but that you can actually direct click on things and manipulate objects. Do you know what this is? It's in the title of my talk. This is Microsoft Bob. So in '95, Windows also wanted a graphical user interface and maybe took metaphors just one step too far. If you wanted to, for example, check your email, you had to look in, well, email not, but check your correspondence. You could click on this letterbox here. If you wanted to write, you had to pick up the pen. It wasn't really a success. All right. But moving on, and now I'm moving into this field of ubiquitous computing. And what's that? So I just told you we were 1968. I'm now fast forwarding to 1988. Do you know what the most popular computer was? What was available in most Belgian households and actually in the wide world in 1988? You may think the Apple, but actually it was the Commodore 64. And average households were still interacting with computers by using BASIC, yes? So not even command line interfaces or menu-based interaction. But at that time, there is this guy, and he writes a paper, and he envisions the computer of the 21st century. Yes? And he explains how he envisions computers to be of all different sizes, to communicate with each other wirelessly, and especially they can become very small, and they can be weaved into the fabric of everyday life. They can become embedded. And if you know, if maybe you've seen the name already here, but so this is Mark Weiser. Oops. And again, you can think, okay, nice, this guy writes this visionary paper, but he was also chief strategist at Xerox PARC, was able to get a lot of investors and computer scientists in Silicon Valley inspired by this idea of maybe computing should become really small. And he also pushed for the fact that if you talk about performance, you should no longer talk about processing speed and these transactions per second, or the 1,000 instructions per second, or the millions of instructions per second. You should actually talk about the number of instructions per unit of energy, per joule. So he really stimulated an entire generation to think about, okay, how can we do low-powered computing? And how can we actually miniaturize computing? And that, I'm skipping, I know, but together with a lot of other evolutions, you come in this era of context-aware interaction with gesture-based and sensors, and so you no longer have to move a mouse. You don't have to use a keyboard, but you don't have to move a mouse either. You can gesture, it infers your context, and you get this what we call natural user interfaces, where users are not even aware of the fact that they are interacting with a computer. They have this tag somewhere, and they just slide it, and they go about their days. So that's this ubiquitous computing paradigm. All right. So we're moving to 2020, where we are now at this moment, intelligent computing. It's always difficult to predict the future, and I agree. So in the title of my slide, I also mentioned Google Gemma. I don't have to tell you that at this moment we have this explosive growth of research and applications that deal with machine learning, deep learning, large language models, and so on. It's what's happening now at this very moment. And you see all of these interesting new products and new types of interaction coming forward. Copilot, probably all of you know and maybe use it quite intensively. And you could think that this new paradigm that's been brought forward or that's been enabled by this artificial intelligence that we see, that it's sort of this idea of giving you a co-pilot or a butler or someone to help you, to assist you. But maybe that's a too simplistic view of it. Because actually this idea of having an assistant or a co-pilot, I mean, we had that 20 years ago, right? Clippy was not always that popular. So it's, you know, it can become very quickly very annoying to have this assistant helping you out. But for some reason, our society has embraced and has been taken aback by ChatGPT. Yes. And if you read articles and interviews with the researchers that have been spurring OpenAI and ChatGPT, it's quite interesting. And I'm not talking about Sam Altman, but there's someone else here that I would like to promote. They mentioned, well, OpenAI, actually, it was founded in 2015. And so for the past 8 years, they had already been, they put forward different large language models. And you had GPT-1, you had GPT-2, you had GPT-3, and GPT 3.5. And ChatGPT was basically just one more polished iteration of this OpenAI large language model, but all of a sudden, everyone knew it and wanted to use it. So what changed? What did ChatGPT write that Clippy didn't do right? Yes. And by the way, do you know his name? So his name is Jan Leike. Yes. In interviews, he explains that they used RLHF. Have you already heard of this technology? It stands for Reinforcement Learning from Human Feedback. Basically, what they did is they showed the answers of ChatGPT to groups of humans and asked them whether the answer was along with their intent. So, very fancy term for, actually, we need to ask humans whether they actually like this answer or not. Of course, they did it at a large scale, invested huge sums of money, but they really worked on how can we make sure that when users are conversing, when they are instructing, that we can infer intent and can give answers that appear magical. So, yeah, wrapping up, we are now in this interesting age, and I also attended the session of Jeroen Baert, where there was also this discussion of artificial general intelligence or super intelligence, this idea that in the very near future, artificial intelligence will be at a level that it will surpass human cognitive abilities, and maybe it will sort of run away and we will no longer be able to control it, and it might harm humanity. Yes. So in response to superintelligence, what has the field of human-computer interaction been doing? Well, there's actually a lot of talk also about super alignment, and I don't know if you know this guy. No? Yes, yes, very well. I heard the name here. Yes, Ilya Sutskever. So at OpenAI, he was made chief executive to lead the research team to make sure that there was super alignment, that actually these advanced AI systems, that they would be designed with human values, human goals in mind, and that they would that we would make sure that they would do no harm and that they would not become uncontrollable. I'm speaking in the past tense because actually after 6 months, well, OpenAI actually decided that they would spend 20% of all research efforts on this, but after 6 months, drama happened and Ilya and his team, also Jan Leike, got fired or resigned. You can have debate about that, but there is no longer that team, that researchers, and ensures that at least with respect to OpenAI, there is super alignment. What can we do about that? Well, luckily there are other researchers in this field, and at different levels in the academic research group of human-computer interaction, a lot of researchers are looking into AI and how can we make sure that AI is explainable? How can we make sure that AI, models of AI, that we can understand them, that users, that there's a human in the loop, that it is trustworthy. I don't have time today to go over the different research groups, but definitely we have quite some impressive professors here that focus on this alignment idea and explainable AI and trustworthy AI. So I invite you to take a look at the website and to come talk to us. And with that, I thank you.
And then, last but not least, we have Professor Giovanni Samai. Giovanni obtained his PhD from KU Leuven and has been a research professor in the department since 2011. Next to research and teaching, Giovanni also has an extensive track record in science outreach and science popularization. He's a member of the numerical analysis and applied mathematics section of the department. He will talk about his mathematical dreams and about futuristic supermodels.
Okay, thank you. Thank you for the introduction. Indeed, I regularly speak to general audience and to high school students. When I do that, it's typically on invitation of their teachers. And so they know that I will talk about numerical analysis, computational mathematics. And so my first challenge is to make them listen. Because I think as soon as I can make them listen to the first few minutes of the talk, I can get them interested into this topic. And that's why the title contains the word supermodels, because I think everybody can have an image of a supermodel in their head, not an image that I can safely show in a school environment, for instance, without getting criticism. So I'm going to talk about other types of models, of course. I'm going to talk about mathematical supermodels that we use to do computer simulations, and these computer simulations can then allow us to do virtual design, to do monitoring of online systems, or online monitoring of real systems, characterization. And the image that I like to use to describe what we mean with a model is the image, well, you recognize the picture, La Trahison des Images, the painting by Magritte of a pipe. And that actually captures very nicely what we mean with a model of reality instead of reality itself. This is not a pipe, it's written below in French. For people, I know that I'm at KU Leuven at the Flemish, but this is French. So, but this was shocking at the time because people say it's obviously a pipe, but why do you write it's not a pipe? And it's because it's an image of a pipe. It's not the three-dimensional object. It's two-dimensional. It's flat. You can smoke it. You can't smoke it. Maybe once, but then it's gone. And so it can allow you to think about what a pipe would be, but it's not a pipe. And the same is true with the mathematical model of reality. It's not reality itself. And Magritte thought he had created an eternal image to highlight this thought. Unfortunately, when I show this in high schools, the children don't know what a pipe is, because this has disappeared from society by now. The three other pictures on the top left, you see an image of a fusion energy reactor that is supposed to be built, or that is being built in the south of France, the ITER reactor. And what is particular about this is, so what you do in this is you create a hot plasma that is so hot and under so high pressure that you want to make nuclei of atoms collide. And with this collision, you get a mass defect that then transfers into energy. The point is that this is very difficult to build, and it's very difficult to know what to build before you build it. So what people do is they do computer simulations with partial differential equations describing individual atoms, individual interactions between atoms, before they actually build this, because it's kind of a multi-billion-dollar project, and you don't want to build something that then turns out not to work because you didn't test, and you can't test, so the only thing you can do is simulation. That's one application domain of mathematical modeling and simulation. The bottom left is a bridge, and what I wanted to highlight here is that also, so a bridge has been designed based on mathematical models that describe how it will vibrate, how much load it will support, etc. But that's not where it stops, the use of mathematical models, because once the bridge is built, you definitely want it to remain operational. You don't want it to collapse. Sometimes it happens, like we had a few years ago in Italy. The day after, my son took a kazoo camp and went over that bridge, so this was very, suddenly this was close by. But the point is that at some point, you want to measure what the bridge is doing, and you want to compare this to what the simulation model tells you, to then, based on the differences, try to guess what is going on, if the bridge is still the bridge you built, or if it has changed, and if it has changed, where did it change, and can you then do maintenance? Why is this important? Because people want to spend the least amount of money and time on maintenance that they can, because somehow you're more popular if you can build visible things, and maintenance is invisible, and therefore a little bit less popular than building new stuff. The same is actually true with doing applied mathematics to make computational models. The mathematics in all of these applications is typically hidden, and so it's often less popular to work on these things than on the visible applications. And the third image is a heart, and that's about characterization. If we have models that describe how electrical currents flow around the heart, we can make measurements on electrocardiograms that tell you how the heart is beating, and based on differences between what you measure, you can try to infer if there is scar tissue on the heart, for instance, to then know where you need to perform surgery. And this is a project that we're currently working on. So I can use this. In the past 50 years, we've seen tremendous increase in capabilities of such computational tools, and I will show you in a few applications. The point I want to make with this slide is that people have been working for decades on problems. I will not go through the technical terms. Computers have become faster over the decades, and so these hardware improvements have led to many, many speed increases in solving such computational problems, but also the algorithms have improved a lot. And you can mathematically prove efficiency increases due to algorithms, and that's the second column. And the point I want to make is that in many applications, and of course on the slide I only show those applications, in which the mathematical algorithms and the software actually contributed at least as much to the speed increase as the hardware itself. So this is something people often don't realize. They think we can compute more because we have faster computers, but we also have faster algorithms. And if we would only have faster computers and with the same algorithms, your speed increase would be the square root of what we have seen. And I'm not taking the most impressive, because this would be a completely ridiculous number, which it actually is. But if you just take this third line, if you multiply these two numbers, you see that we can bring down computations that would have taken 180 years before to about a second now, just by the combination of hardware and software improvements. And I will show you one example of such. I'm not going to go through all of the applications and things in the group. I will just show one example that Stefan will know very well, because it's a collaboration that he started with the bioengineering faculty. It's on the storage of pears. So this is something that you should wonder. Pears are ripe in the fall, but you can buy them in the supermarket all year long. And the question is, why is this? And it's because they are typically harvested. I was going to say pulled from the tree, but they are harvested just before they are ripe, and then they are kept into some protective environment, and then they are gradually released to the supermarkets so that we have pears all year round. And so what Stefan has done, or Stefan's group has done, together with those bioengineers, is to simulate how the ripening process of these pears acts, because what you can have as accidentally, and you've probably all seen this, if you have a conference pear and it's not ripe yet, and you cut it open and it's already brown in the middle. This is a disease that you can prevent or provoke based on the environment that you surround the pear with. Now, the next problem is that no two pears are the same. They all have slightly different shapes. They are at a slightly different stage of the ripening process, so you also want to quantify uncertainty on the ripening process to have probabilities of pears being diseased or being ripe. And we have a YouTube video from which I've taken this screenshot that shows how you can actually speed up computations quite dramatically. I'm just going to show the basic principle. This is multi-level Monte Carlo. So the idea is that if you want to have a prediction of the probability of ripening of rotting of a pear, for instance, you need to do many, many pairs, and then you need to look at the fraction that has become ill or take some mean or something. And each individual simulation is quite expensive already. As I've told you, that's what they worked on before, making this individual pair simulation faster. But you need to do many of those. So what you can do is you can say, what we can actually do is we can have a very inaccurate pair, and we can make it slightly more accurate, slightly more accurate, slightly more accurate. We can do many of those, and then we only need to compute differences. And to make differences more accurate, you only need to do a few differences, because the difference is small, so you can have this accurate really reasonably quickly. It's explained a little bit more in this video. I will skip over this. The point that I'm at now is that you might think, they can do a lot now. There is no future anymore in this field. Why are you here talking about the next 50 years? Of computer science, everything is done. But that's not the case. And that's not the case for two reasons. First reason is that, and this is an image that is taken from a video that you can watch online. It's my lecture for the Universiteit van Vlaanderen, in which I talk about computational complexity of climate simulations. It's to show that mathematics is important in such fields where the only thing you can do instead of an experiment is waiting, because if you want to know what the climate will be like in 2100, and you can't really build a small planet to see what's going to happen, you can't do an experiment. So the alternatives are computing or waiting. And then I basically explain that there is some uncertainty with these predictions. And then you get people on YouTube complaining. You see, even the scientists don't know for sure what's going to happen with the planet. We don't have to trust scientists. So now I also stress in my public lectures that not only mathematics is important, but also comprehensive listening. The point I want to make here is that if you want, people typically, as soon as they get a faster computer, they want to solve a bigger problem. That's human nature. And so people say, your computer is 10 times faster, let's make the grid 10 times smaller in each direction. But if you do that, what we need is, for the climate model, we need temperature in each of the boxes that we are computing, because it's a function of space, but you have to discretize. So only a finite number of points in space. Let's make the number of points in space, and not only temperature, but also air pressure, humidity, etc. So a number of variables per box. If we make the box a factor 10 smaller, I've drawn a factor 2, because otherwise you wouldn't see anything. If you make it a factor 10 smaller in each direction, it's 3D, so that's already a factor 1000. If you then think about the time step that you need to take to do simulations, just think of a cloud, for instance. You would want to be able to track a cloud from one box to the next. So your time step will need to become 10 times smaller also, just because your grid is 10 times more refined. So that's already a factor 10,000. If you then know that climate models are run for 3 months now, just to see what's going to happen, the 3 months times 10,000, we are again in the 180-year ballpark. And I've now just assumed that the computational cost is linear in the number of unknowns. So twice as many unknowns, twice as many work. That's usually not the case. Usually, for one of these grid points, you need to do something with all the other ones. So then you get 10 times the amount of cost, or 10,000 times per grid point. And there are 10,000, so it's 10,000 squared, the cost that increased. So we need to be smarter than that to actually advance. And that's not all, because human ambition really has no bounds. And what people say, we don't want to do one simulation. We want to do many, many more simulations. So certainty quantification is one example. I didn't track my time, so just warn me. I'm going to start the video already. People say, what we can simulate is the ocean currents, for instance. But what we need to have for ocean current simulations is the initial condition. We don't have the initial condition because we only have a number of measurement stations. So we fill in something in between, and we can do this in multiple ways. And so this is how we have uncertainty quantification. But what sometimes can happen, you can look at the movie at the same time. Sometimes happy accidents happen, like this crash or a loss of a container full of rubber ducks in the Atlantic Ocean. This happens because apparently it's cheaper to overcharge boats systematically and now and then lose a container than have an extra boat. So that's economics, that's not math. But so these rubber ducks, they all fall in about the same place in the ocean, and then you see where they end up in different places at vastly different times. And what you can then see is that some of these places will be matching simulations with intermediate values that you filled in, and others don't. And this way you can gradually build up knowledge about your initial condition and gradually increase the fidelity of such forward simulations. And this is so successful that people are using, you've seen it in a movie, people are using everything that falls into the sea now, and that's a lot. Lego blocks, football gloves, Nike Air shoes. And that's actually fun because people found Nike Air shoes, and when they dried them, they were perfectly wearable, even after 5 years in the ocean, so perfect material. You, of course, have to find 2 identical ones, and that's not as easy as it looks because they are anti-symmetric, so they drift apart in different directions. And actually, that also has been studied with a boat that has crashed, basically full of shoes in the channel between the UK and France. And all the left shoes ended up in Ireland, and the right shoes ended up in France, and so they simulated why. Okay. And such problems are in fact ubiquitous. I've shown about the climate, I've shown about bridges, I've shown about cardiac modeling. There is also work in our department, in the group of Martin Thiel, ongoing on material design for new batteries, so to make battery storage, to make the materials capable of storing more energy per volume. Drug design, virtual drug design, wind farm, green energy. Because this is a difficult problem. If you have a wind turbine, it's typically difficult to find the location where you can put one without anyone complaining. So if you find such a location, you want to put more than one. But if you put more than one, you have to put them in such a way that, because you can only extract energy that is in the wind once, so if you put the second one right behind the first one, it will not deliver anything anymore, so it's a wasted investment. So you have to optimally position, etc. Also, this is being simulated before they are built, because otherwise it's a waste of investment. So what is now ahead of us in the next 50 years, beyond simply improving the algorithms that we're currently working on with traditional techniques? AI is a very big thing. We've seen a number of talks already now. I'm going to show you here with this example. So these are Kirchhoff laws. They can be used to simulate electrical circuits. But such an electrical circuit, like the electrical network over the US, is very difficult to model at such detail. And for instance, also because we don't know when people are switching on their light, or when, let's say, the example that I gave in high schools 5 years ago, of which I hoped it would be no longer current, was the hair blower of Donald Trump. You don't know when he will put it on, but unfortunately that's still an actual or a current reference. So what people do is they measure as a function of, this is the days of the week, and this is the time of the day. You see the weekend, lots less consumption, and then in the week, it depends on the time of the day. And so people make data-driven predictions of demand on the electrical network. that can supplement physics-based models. That's one approach. This is on the software side. On the hardware side, we have these supercomputers. This is Lumi. This is one of the biggest supercomputers we have in the world, but there are also new architectures appearing. People tend to move towards graphical processing units, GPUs, to speed up AI-type simulations, and also quantum computers are a hype now. So there is a new professor in the group that will work on algorithms for quantum computers in the future. So that's, I think, where we're going. We need to embrace AI, and we need to always be aware of changes in hardware that influence the algorithms. So if we then look at where we come from, and this is a picture I took from the archives of Jean Huns, on the very first computer that was in the Department of Computer Science, that was also used for numerical simulation. I think we've come a long way, and more is yet to come. So I thank you for your attention.